Maybe I'll wait a couple of minutes.
Can I
Some
hide these panel things which are floating? Hide floating.
Sorry?
You should be able to move them around. We don't see them on our end.
Oh, you don't see them? Okay.
Okay.
Can I hide these panels?
There is an option if it's the floating controls on the dots. There's something about hide.
Yeah, no, I did that. But I think it just pops up every time I speak. So maybe there is something.
We're already live, Shashank, if you want to take it away.
Okay. Hello, everyone. Thank you for joining us today for the last EPSP Connect seminar of the fall semester before we all head out to AGU. The purpose of this series is to bring the community together and to help establish connections between people who might not be able to interact with others in a different setting. So we are very happy to have you here. First of all, I would like to thank all the EPSP Connects team members who help plan and organize this series, reaching out to potential speakers, coordinating with them, and also advertising it in the social media and making sure that the series information is up to date on the website. Regarding the Q&A, Tyler Doan, one of our EPSP Connects team member, will also help us in the end. Please put your questions in the chat. We'll monitor them. And if you prefer, we will be able to ask you to unmute and ask the question directly. And for those people who are listening us on live stream via YouTube, we'll also keep an eye on the questions there. Today, our speaker is Dr. Arvind Singh. He is an associate professor at the University of Central Florida. His research interests are in the area of hydrology and geomorphology. He's an expert in sediment transport, and his contributions to the study of statistical mechanics of sediment transport and its interaction with flow regimes have been widely recognized by the hydrogeomorphologist community. And his current research focuses on linking and modeling interacting processes such as fluid flow, topography, material flux transport over a range of spatial and temporal scales. So, Dr. Singh, please take it away.
Okay. Thanks, Shashank, and thank you, everyone. Good morning. Good morning. I'll be talking about the connectivity in patterns and processes of river networks across scales. The picture on the left is from a landscape, from two different landscape exhibiting humid versus dry environment basins. The picture on the right is from physical experiments that we conducted at the St. Anthony Falls Laboratory, where we can see the evolution of networks as the precipitation and uplift come in play the role. The question with the specific question: does topology or connectivity influence structural and functional complexity of a river network? So this work has been done in collaboration with graduate students and postdoc here at the UCF, as well as some collaborators within and outside the UCF. My research group's main focus is on identifying understanding the response of landscapes to changing. I see this panel on mine. Let me hide it. So as I was saying, my group focus is on the response of landscape to changing precipitation patterns, with the focus on understanding how these changing frequency and duration of these extreme events affect the floods, the infrastructure, as well as vegetation and overall the landscape. So with a specific question as how does changing precipitation pattern affect landscape evolution and sediment transport? Is there a signature of extreme events on landscape, and these extreme events could be short-term or long-terms, and can we quantify the potential of landscape reorganization under changing forcings, such as changing the climate during steady and transient conditions? So today's talk, I'll be more focusing on identifying or focusing on connectivity with particular questions such as, can we identify the signature of varying climate from geomorphic and topologic properties of landscape and its river network? Does the topology or I see some things on my screen and like I have to cancel it every time. So again, the questions are, does the topology or more specifically the degree of side branching influence the structural or functional complexity of river network? And what physical processes or features contribute to increasing complexity on the landscape? And how does the complexity or connectivity in general in river networks relate to dynamic connectivity? So drainage density has been used as an important geomorphic feature to understand the response of climate on landscape. However, drainage density exhibit U-shape type of behavior with increasing precipitation. So for example, drainage density has been shown to increase with increasing climate and also with decreasing climate. And from this particular figure, if we see if it exhibit a U-shaped type of behavior or nonlinear behavior, we can get two different landscapes from very different environment exhibiting the same drainage density. So for example, a landscape can be from humid versus from dry, which can exhibit same drainage density. So our question is, are there other signatures on the landscape that can tell us about the climate, or in other words, like, can we identify topologic or other topologic or geometric measures from the topography or the river networks to identify the signature of climate? Similar observation of increasing or decreasing drainage density has been observed from physical experiments as well as numerical simulation. In this particular numerical simulation, with increasing D and K that mimic the increase in precipitation, or with decreasing D and K that mimics the decrease in precipitation, we can see there are variable patterns of drainage density. Similarly, from physical experiments, what we have observed is that with increase in precipitation, the drainage density decreases. To explore the role of climate on the connectivity, or if there are signatures of climate on river networks, we can quantify the topology of a given network. In this particular case, here this is a simple example or a schematic of a river network where the branching can be defined as two channels of same order merging, whereas side branching can be defined as two channels of different orders merging. And we can explore how the percentage of branching or side branching, or in general, like how like how much influence does these branching versus side branching has on a given network in terms of climate or in terms of complexity in river networks. So for that, we use to quantify this side branching percentage or side branching in a given network. We can use Tokunaga indices or Tokunaga model, which is given as Tk equal to ACK minus 1, where K represents I minus J, and I and J being two different orders of a given network, where J is greater than I. And the parameter C tells us about the degree of feathering, that is, how much side branching do we have in a given network. So for example, if we use these AND members, where on the left shows a network which is exhibiting purely branching type of structure, and on the right, which is exhibiting the purely or the most possible side branching type of network. In the case of purely branching, the C value, the computed C value should be equal to 0, whereas in the case of purely side branching, or most possible case of side branching, the C value should be finite. So in other words, if you have a branching network or branching system, this should have a C value, that is the feathering coefficient should be equal to, or feathering parameter should be equal to 0. So when we extract the river networks from different basin exhibiting different climate aridity index or mean annual precipitation, what we observe is that the C value that again expresses the degree of side branching in a given network increases with increasing mean annual precipitation. Similar observations of C value trend with climate has been also observed in the previous literature. For example, Zanardo et al. Showed that the C value has a strong correlation with climate aridity index, which is essentially the ratio of potential evaporation to the precipitation. So here what we see is with increasing mean annual precipitation, the C value increases, and that tells us that the degree of side branching increases within a network when we increase the precipitation, or the channel becomes more heterogeneous, or channel network becomes more heterogeneous with increasing mean annual precipitation. So to explore what is the role of this heterogeneity or this side branching in river network complexity, we use the width function. So we take two different networks two different networks exhibiting same drainage density, but coming from very different climate, one coming from dry and other coming from humid. And we compute the width function, which is essentially the number of channels intersected as you move from downstream or channel outlet towards the channel head. And it gives you some information about the organization of channels in a given network as you move upstream. So to understand how much complexity does these channels introduce or impart to the channel network or to the structural arrangement of the channel, we use complexity concept. And complexity concept has been used extensively in the literature, specifically the Shannon entropy. However, Shannon entropy only characterizes the distribution of a sequence. For example, if I look at these two different networks, which have the same drainage density, however, they have very different channel network patterns. And when we compute the width function, although shows the same distribution, but has a very different pattern of how many channels we are intersecting at a given distance. And if we compute the Shannon entropy of that, the Shannon entropy will be same because the distributions are same. So for that to overcome this limitation of Shannon entropy, we use sample entropy, which takes into account the spatial arrangement of channels in a given sequence, or which characterizes the spatial arrangement of these channels in a given sequence. And here the time series of this width function. In other words, width function gives you some information about how the two-dimensional spatially explicit river network can be represented in one-dimensional signal. When we do the sample entropy of these two different networks exhibiting same drainage density and same distribution of width function, we see distinct values of sample entropy, or the sample entropy is able to characterize this. For example, if we look at these two simple examples, X and Y, in X, we have the patterns that are repeated, whereas in the Y, the patterns are not being repeated. So the sample entropy is very different in case of where the samples are, where the patterns are repeated versus when patterns are not repeated. And we also compute this sample entropy at multiple scales, since the river networks exhibit a multi-scale type of behavior. And we call that as multi-scale sample entropy. So here, if we compare the river networks extracted from two different climates exhibiting same drainage density, and we compute their multi-scale sample entropy, or the sample entropy at multiple scale, we see very distinct behavior in case of entropy. And here, for this example, what we observe is that the dry basins exhibit higher complexity as compared to humid basins. And this particular complexity is purely because of the channel network arrangement. To take into account how much complexity does the hill slopes introduce to these landscapes, what we do is we take into account, or we use incremental area function, which essentially tells you about how much drainage area we are accumulating as we are going from upstream to downstream, from channel head to the channel outlet. Incremental area function is essentially the difference between areas at a given distance as you're moving from upstream to downstream. So in other words, width function gives us information about the structural arrangement of channels, whereas incremental area function gives you information about both the channel network arrangement or channel networks as well as hill slopes that are contributing to that particular location where the incremental area is being computed. So from that, we can also compute from width function and incremental area function, we can compute the structural complexity, which essentially is which essentially characterizes the patterns in the structural arrangement of channel, and the functional complexity as the drainage area represents the patterns of or may represents the patterns of flux propagation, as drainage area can be a proxy to the discharge. And we analyze these networks which were extracted from different locations exhibiting different climate aridity index using multi-scale entropy or sample entropy. And here is a plot between entropy and C value as a for width function and incremental area function for different scales. So from this particular figure, what we can see is that if we plot the entropy for entropy as a function of C value, again, entropy characterizes the degree of complexity, whereas C value characterizes the degree of heterogeneity. So what we see that there is an increasing trend between entropy and C value for both width function and incremental area function. And a few observations, if you look at these plots, a few observations can be made. For example, in the case of width function, if we compare the y-axis of width function with the y-axis of incremental area function, the entropic content in the case of width function is much smaller as compared to the incremental area function across all scales. Also, the slope of the entropy versus C value is also smaller in case of width function as compared to the incremental area function, which you can see from the computed linear regression line. So to see how these slopes are changing or before, like these particular observations suggest us that the complexity in the system or in the network increases with increasing side branching. As we can see, the slope is not that different in the case of width function as compared to the incremental area function. And this we can clearly see when we plot for different scales or across scales, the slope between entropy and C value for both width function and incremental area function. And so from here, what we see is that the width function, the slope is much smaller as compared to incremental area function. And the increase in the slope is also smaller as compared to, in the case of width function, as compared to incremental area function, suggesting that side branching is introducing more complexity in incremental area function, or side branching is introducing more functional, more complexity in the functional processes as compared to the structural arrangement of channels. As we know that width function only characterizes the channel network arrangement, whereas the incremental area function gives us information about both the channel network as well as the hill slopes. We can compute the differences between the width function slope and the incremental area function slope, and try to understand what is the role of hill slopes or side branching in introducing complexity to the hill slopes as a function of scales. So when we compute the difference, what we see that this particular change increases, or the change in slope increases with increasing scale, and at a certain scale it peaks up and gets saturated. And this particular scale is on the order of 45 to 50. And again, these observations have been taken from more than hundreds of basins. From an independent analysis of hill slope length, what we computed was the hill slope length for all these basins, and what we observed that the average hill slope length, which is the inverse of the drainage density, is on the order of like 55 or 56 meters, which indeed emphasizes that the hill slopes contribute to more complexity, and it increases as we move towards the hill slope average hill slope length, and it saturates. So in other words, the side branching introduces more complexity to hill slopes as compared to channels. From another analysis where as we know that on hill slopes, the diffusion is the predominant factor. We computed diffusion coefficient of these topographies and plotted them as a function of C value. And what we see is there is a positive correlation between diffusion coefficient and C value, suggesting that indeed the diffusion coefficient increases with increasing heterogeneity or side branching in a given network in a basin. So in short, what we observe is that the channel network's flux transport patterns are more complex than the structural organization of the channels, and they both are controlled by topological connectivity, or that is the degree of heterogeneity what we observe in a given network. So far, what we have talked about is a given network, how these channels are arranged on that particular network, and what is the role of side branching, and how this side branching changes as a function of heterogeneity. So these are static sort of networks. We want to explore how does varying network topology, that is side branching or branching, which are a signature of climate on river networks, facilitate the flux transport, or in other word, does the transport process or the fluxes that are moving on a given network have some signature of these feathering or side branching or climate. So for that case, we can again use this connectivity structure where we can define the channels, branching channels as the channels merging of same order, and side branching channel as channels merging of different orders. And we can introduce clusters which are defined as a set of connected elements that are disconnected from other elements in the system, and introduce flux propagation processes based on dynamic connectivity of these clusters. So that is how these clusters, which are defined again as the elements that are connected, how these clusters evolve as a function of time with different with different transport processes. So for that purpose, we define two different types of connectivities. One is dynamic. One is based on dynamic clusters and structural connectivity. The other one is based on a flux aggregation or time of concentration. So in short, what we analyze is two different patterns. One is based on minimum connectivity. That is when the river network is connected at the minimum flow condition. And the other one is when the river network or when the clusters or the network is connected when you achieve the maximum flow or the peak flow at the most downstream element of that particular cluster or a given network. And we refer to that minimum connectivity as DCS, whereas we refer to the maximum or the peak connectivity as DCT. And we look at the evolution of clusters as they merge or as the fluxes propagate from upstream to downstream in a given network. So here is an example of a given network. We refer that to a static network that can be extracted from a given basin. And we propagate fluxes from sources in two different manners as described previously based on structural extent or the minimum flow connectivity and based on the peak flow connectivity. So here in this particular example, which represents 16 source nodes, we'll see how the fluxes propagate and how the patterns are different of connectivity as the fluxes propagate from upstream to downstream. So starting with 16 nodes or 16 source nodes, in both cases, when these fluxes propagate downstream, assuming a constant velocity in this particular case, because we are analyzing the effect of topology on flux propagation, assuming a constant velocity and unit length of these links or channels, what we see at time instant 2, there are 12 clusters formed in both cases, which are defined so that we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 clusters in both cases. As we move further down at time step of 3, the number of clusters changes in both cases. And in the case of DCS, the number of clusters is 4, whereas in the case of DCT, the number of clusters are 9. And as we go further, we see that we have achieved the full connectivity in the case of DCS, that is from the point of minimum flow condition, all these channels are now connected, whereas DCT is still not connected at that particular time instant, and it takes longer to connect the whole network from the point of maximum flow or the peak flow, that is the peak flow at the most downstream end. So in other words, for the case of DCS, from the same static network, we take 4 steps to achieve the full connectivity, whereas in the case of DCT, we take 8 steps, almost double the time for this particular connectivity. And we analyze the role of branching and side branching on the patterns of flux propagation. So in the previous slide, what we are looking at is number of clusters at a given time as they are propagating, as they are merging. The flux is propagating downstream. So here, to analyze the effect of side branching or branching or network heterogeneity on the connectivity patterns, what we do is we create synthetic networks and 2 end members, one exhibiting perfectly branching structure, and the other one exhibiting the most possible case of side branching structure, which is represented here as SBR or E. And in between, we vary the percentage. We generate several other networks. Here, for example, I have shown 3 networks where we vary the percentage of side branching or branching in those systems or networks. And what we observe, that is the number of clusters or DCS as a function of time, as well as DCT, exhibit different kinds of patterns. So for example, the DCS, in the case of DCS, what we see is that the network which exhibit the most side branching connects fastest, whereas the network which shows most branching type of structure takes longer. And we can normalize it to constrain or to compare different networks. And what we observe that other networks with varying percentage of side branching, they fall in between these 2 envelopes. In contrast, for the case of DCT, what we observe is that it takes the longest to achieve the full connectivity in the case of most side branching cases, whereas in the case of branching, we achieve the connectivity the fastest. And all other networks with varying percentage of side branching fall in between. So here we analyzed 50 different or more than 50 different basins across the United States. and with varying side branching percentage, because we were interested in understanding the role of topology on flux propagation patterns. And when we look at the patterns of DCS, or the minimum connectivity versus maximum connectivity, that is DCS versus DCT as a function of time, what we observe is that these networks place them into two different subsets, or there is an emergence of two subsets, one depicted by these pink and purple lines. And for reference, we have plotted the envelope uh, for the case of purely side branching, and for the case of purely side branching systems or networks. And what we see is that the pattern of flux propagation is very different for these two different subsets, where the purple line exhibit higher side branching or have higher side branching ratio, whereas the pink line has, pink lines have, pink curves have smaller side branching percentage. For the case of DCT, we see a similar type of behavior, and these envelopes exhibit or show the branching versus side branching ratios. For the case of DCT, we see some separation of two different sets exhibiting different side branching, but the separation is not that clear. To further explore the differences between DCT, or the evolution of clusters, number of clusters as a function of time, what we do is we take these curves, or DCT curve as a function of time, and we integrate the area, and we refer to that as integrated connectivity rate. And what it tells us about is like how the connectivity or how the channel networks are connected uh, as as you are propagating fluxes from upstream to downstream. Or in other words, the networks with higher, in this particular case, what we would expect is that the networks with higher side branching exhibit slower convergence of fluxes, or higher, if the ICR or the integrated connectivity rate is higher, uh, that should exhibit a higher side branching. So when we plot the ICR as a function of side branching percentage, what we see is an increasing trend of ICR with side branching, again suggesting that the connectivity rate or this ICR increases with increasing side branching. However, there is some sort of scatter around the trend line. To see why we observe this scatter, we look at the basins which exhibit same side branching but different integrated connectivity rate. And what we observe from there is that if we look at the basins which exhibit higher connectivity rate as compared to lower connectivity rate, these the one with higher ICR exhibit some sort of, or show some sort of elongation of basins. Or in other words, these basins are relatively elongated as compared to the one which is having a small ICR, and they both have the same side branching percentage. On the other hand, when we compare the networks with, or the basins with same connectivity rate, but with varying side branching. So in case here, third is basin 3 is exhibiting lower side branching percentage, whereas basin 4 is exhibiting higher side branching. We observe that in these particular cases, the subbasins are more elongated as compared to the basins. Or in other words, the subbasins get elongated if we increase the side branching much more, keeping the same ICR. So far, what we have looked at here is essentially how the number of clusters are changing or evolving as a function of time. But these clusters also have magnitudes. That is, we can define how many sources are contributing in a given cluster, and we can explore how these clusters are spatially distributed on a given landscape. Or in other word, we can explore the role of topology or climate on spatial distribution of clusters. So here, if we look at a given network, and instead of looking at the number of clusters, we look at the magnitude of each clusters, and see how many clusters, how the magnitude of cluster is changing as a function of distance. Here, assuming a constant velocity, we can interchange the velocity and time. So how, when these clusters merge and they form larger clusters as you move downstream, we can look at the distributions of these clusters as a function of distance. And here is a sample example where the magnitude of clusters is presented as a function of distance. And here the distance is defined as the normalized distance, and normalized in a sense that the distance divided by the distance to achieve full connectivity in the system or the network. And here we are more focused on analyzing the patterns based on DCS, that is the minimum connectivity, because that particular connectivity or DCS tells you about more information about how the connectivity is emerging in a system. So we analyze these magnitude of clusters as a function of distance, and what we observe, if we look at the distribution, that this distribution changes shape as a function of distance. And in fact, the distribution at a given distance, or at a distance d, is exponential, and it changes to power law. And this is a signature of critical phenomena, or so-called phase transition. Phase transition, where we see a change in the properties or a distribution of a function as you move from as you start accumulating clusters, or as you move from one scale to another. So in this particular system, what we are observing is phase transition. And at phase transition, what we observe is the power law, or the change in distribution from exponential to power law, and also the presence of a giant cluster. The giant cluster here is defined as the largest cluster at the phase transition, which will remain largest throughout the evolution of the network or the whole cluster formation. So until this cluster forms, the whole network is connected, this cluster will remain giant, or giant cluster. In other words, we can see from this particular analysis, we can see how the clusters at different distances are merging and forming. So for example, for this given network, we have at distance d1, we have all the sources present in the system at distance, and another distance d2. Then these sources forms clusters, or form larger clusters, and another distance d. If you compute the distribution is exponential. And at DC, you have more connected states. So in other words, in the case of like when we observe this exponential, we have a sparsely dominated or sparsely located clusters of varying magnitude. Whereas in the case when we see power law type of distribution, that suggests that we have more congested clusters which are more organized on the landscape. So here, this is again for this particular example, this is the magnitude distribution, and at two different distance, D and DC, we observe exponential and power law type of distribution, and we call this as distance DC as the critical distance. That is the distance at which the power law is observed. When we compare these distribution when we compare these distributions with as a function of climate. So for example, the upper one is for a humid environment, whereas the bottom is for a dry environment. We observe that the distance at which the phase transition occur is much smaller as compared to the one in the case of dry. These distances are different, and in fact the computed exponent of these power laws are also very distinct and different. So to first understand why this phase transition is occurring, we create synthetic network and try to analyze the role of side branching on these particular cluster formation, or the magnitude of cluster changes as a function of distance. And in short, if we take a network which is purely branching and has uniform link length, then there will be no phase transition. So it suggests that the heterogeneity, which could be due to side branching or could be due to geometry in the link lengths or in the network, could cause this phase transition. So to compare or to see how this climate affects or if the climate has a signature on this phase transition, we analyze more than 100 basins across the United States and compute the distance and the power law exponent and see if they have relation with topology and so on. And as we have seen in the past, there was a dependence of C value, that is the heterogeneity or side branching, as a function of mean annual precipitation. We also observed that the link length extracted from the river network is also smaller in the case of humid basins as compared to dry basins. And we know that a link length distribution exhibits some sort of exponential distribution or exponential shape. If we look at the mean link lengths as a function of order, we see that this is consistently smaller. The link lengths are much smaller in case of humid as compared to the dry. So putting this information together, if we look at the time at which, or the distance at which the phase transition or critical phenomena occur, and plot that as a function of C value, what we observe is that the dry basins exhibit higher or larger DC as compared to the humid basin. If we plot it with a link length or average link length of that particular network, what we see that there is no clear trend between humid and dry. On the other hand, when we plot the critical exponent, that is the slope, similarly, when we compute the slope or the power law slope and plot them as a function of heterogeneity or C value, what we observe is that dry basins have smaller critical exponent as compared to, or power law slope as compared to, the humid basins. And critical exponent does not have a dependence on the link lengths or geometry. So in other words, the C value gives you information about the topology or the dependence of these critical parameters on topology, whereas link length gives you information about the geometry. So from here, what we can say is that the topology plays a primary role in controlling or resulting in phase transition, whereas the link length plays a secondary role, or geometry plays a secondary role in controlling or in phase transition. And so we analyze these critical parameters as well as the properties such as C values and drainage density as a function of different channel extraction thresholds or scales, in other words. And what we see that this critical distance does not depend on channel extraction threshold, or that is remains independent of the scale. Similarly, C value also, the feathering is independent of scale, and that emphasizes the C value, if it does not change, emphasizes that these networks are self-similar or fractals. However, if we compare the mean between two different climates, humid versus dry, what we observe that the mean distance or critical distance is smaller in case of humid as compared to dry. And similar observation can be seen from similar observation can be seen from the mean C value or the C value as a function of channel extraction threshold, that it does not change significantly as a function of channel extraction threshold. However, if we look at the drainage density, there is a dependence of drainage density as a function of channel extraction threshold, and that's expected because drainage density is defined as the total channel length over the drainage area, and if we change the channel extraction threshold, we change the channel length, although we do not change the drainage area, so the drainage density does change, and we see the dependence of drainage density on the scale. So far, like I know there is a few minutes left. So like we talked about the power law exponent or the critical exponent, the distance at which this exponent or this power law is occurring or phase transition is occurring. If we look at the giant cluster, we also know that at phase transition, there is a giant cluster form that will remain giant or the largest throughout the evolution of the network. And if we look at the spatial distribution or where exactly or where on the network these giant clusters are formed, we can get some information about hotspots on the network where the connectivity is emerged or formed much faster as compared to other locations. So here, for example, for this particular network, we have seen the phase transition changing from exponential to power law, and if we place this particular giant cluster on the network and compare these network with some other clusters of similar sizes, what we observe that there are geometric and topologic differences. So for example, here in the case of gradient, we look at the channel, we look at the profile of this particular or the river profile of this sub-basin and compare with the profiles of the other sub-basin. We see that in the case of giant cluster, the profiles are much steeper. From the point of overall phase transition, what we saw that DC has a dependence with C value and does not depend on the geometry as much as on the topology. If we take into the information from the giant cluster and we compute, since we cannot compute the C values of these giant clusters at the time of phase transition because the Tokunaga analysis will require larger networks and it won't be robust estimation of C value. We take the magnitude of these giant clusters and relate it with the DC, or that is the critical distance at which the phase transition is occurring. And from here, what we see is that the magnitude of giant cluster is increasing with increasing critical distance. And from here, we can also see that this magnitude is small, or this magnitude is smaller in humid basin as compared to dry basin. From the right-hand side, we can also see, if we compare the geometry, average link length is smaller in giant cluster as compared to the overall link length. So on the y-axis is the average link length of the giant cluster, whereas on the x-axis is the average link length of the whole network. We observe that the average link length is smaller in giant cluster as compared to the overall river network, and also is much smaller in humid basins as compared to the dry basins. So these results emphasize or imply that humid basins exhibit more heterogeneous, spatially distributed clusters on the network or on the landscape as compared to dry basins. And this particular approach can be used to identify spatial locations of where we have this faster connectivity on the network. So, so in summary, I see the clock is passing time. So in summary, what we see is that the climate imprints a distinct signature on landscapes in terms of river network topology and geometry. Humid basins are naturally engineered to slow down the fluxes. This particular framework can provide information, which is the phase transition approach, can provide information about critical or important locations on landscape as a function of climate. And we need to incorporate side branching characteristics in hydrologic models for accurate prediction of flow duration curves, and thus for environmental fluxes such as sediment transport or discharge. With that, these are some of the references and the collaboration and the funding agencies. And I would be happy to take any question. And I'll play this video which is from the physical experiment, where you can see how these river networks are evolving as a function of precipitation and uplift and change with changing precipitation pattern. And this particular network is obtained from one of the subbasin. And just to mention, this experiment is 0.5 meter by 0.5 meter. With that, I would be happy to take any questions if there are.
Great. Thank you, Dr. Singh. That was a really great talk. Very interesting. As a reminder to folks, if you have questions, please go ahead and put them in the chat, or you can raise your hand and ask to unmute and ask the question yourself. While we wait for questions to come in, I have one. As I understand it, I could be wrong, but these clusters that you generated are generated by uniform and constant velocity throughout the network. Is that correct?
That's correct. So we assume that we have the uniform velocity. But
Okay.
I mean, we can take into account the variable velocity on the network in the model.
Okay, yeah, that was my question is, do you think would that change the results much, or how important is it?
I would not expect the results to change significantly, because we take into account the changes in the geometry as well by taking into account the link length and so on. So I mean, I would not expect too much changes in short. But this particular velocity or the varying velocity can be taken into account in the model.
Okay, cool.
While we are waiting for questions, actually, I had one. In the first part of your talk, you showed the difference in the slope of, I think, incremental area and the width function saturates at a certain spatial scale for side branching. And I was curious if that scale has a certain physical meaning.
So so here. So that particular scale where we see the saturation is related to the hill slope length scale. That's what I was talking about. That if we compare the relation between entropy and C value and compute the slope and take the differences between the width function, which characterizes the channel arrangement or channel network arrangement in a channel arrangement of channels in a network, and incremental area function emphasizes both channel network arrangement as well as the hill slope. This peaks tells us that from smaller scales to larger scales, like or up to the hill slope length scale, the complexity is being introduced, or the complexity is introduced by increasing the heterogeneity or side branching in the system. And it peaks at that scale, which is similar to the scale of average hill slope length. So if you compute the hill slope length from channel head to the ridge, that's on an average is similar to that particular hill slope length. Is that what you were asking, Shashank?
Yeah, thank you for answering that.
We've had a couple of questions come in. One is from the Penn State Watch Party. How do you account for other factors that influence drainage density and shape, such as lithology or topography that arises from local structures?
Yeah, I mean, so here, of course, like, I mean, we know that uplift rates or different other different factors such as wind or something could affect these drainage density. But the point here, or the analysis we were doing is mainly looking at the effect of climate on drainage densities. And that's why I was saying that when we go out in the field, I mean, if we compare the mean annual precipitations, we can get two different basins which exhibit same drainage densities. But yes, I mean, that's a good question. Like, if there is a varying uplift rate, would that affect the drainage density? However, in this particular experiment or in this particular analysis, the basins which we extracted were of similar drainage, similar uplift rate and less human impact. So the conditions were relatively similar.
I think we have another question in the chat from Vinay, is how to investigate the morphological changes of the particular catchment network under climate change. And I think for morphological changes, he's asking the slope of the channels or erosion rates, and how does those get changes under the particular catchment network under different climate. So it's like future extreme events. And what are the models that we can use to understand these kind of changes?
So if I understand the question correctly, how do we model the changes in the topography as a function of climate? I mean, there are several models, such as we can use the slope area curve of a given system and see how these slope area curves are changing. That could be one of the approach. In terms of dynamic connectivity, there would be an interesting approach. For example, if we look at the dynamic connectivity, which is based on minimum flow versus the maximum flow, what it can give us some information about when it is minimum flow. This DCS may be more relevant for ecosystem diversity under changing precipitation. As changing these precipitation patterns, I mean, they affect the overall or variable precipitation pattern could affect the overall connectivity in these systems, such as ephemerality or a connectivity in upstream channels. Whereas in the case of DCT, which essentially gives us information about the peak flow condition, these might be more relevant for large-scale changes or geomorphic changes, such as the changes in the peak flow or the stream flows, or large scale reorganization of the network. And I assume the question was like mainly for static, mainly for the topography, how the topography change as a function of climate. That was the question. Like, I think I answered about the dynamic too.
Yeah. So I had a question on top of that. Like typically the models use like water flow in a steady state condition whenever most of the models in landscape evolution. Do you think we need unsteady equations of water flow combined with the landscape evolution equations to see the dynamic connectivity changing in short term? Or you think those models are still helpful to see how the changes in climate will affect the certain morphological changes in the network?
So yeah, I mean, if you take into account what you are saying, the changing unsteady water flow condition in a given model, of course, I mean, we should be able to see the change in a landscape as compared to at a steady state, because like this landscape evolution model, I mean, at some time it achieves the steady state or a static steady state. And if you take that static pattern or the pattern on the topography and extract the dynamic patterns, the patterns will not be very different. Whereas if you take into account the dynamic topography, which could arise due to changing this transient condition of water flow on the landscape, could result in varying patterns in terms of dynamic connectivity. And of course, like, will give you better information about how, by changing the system to a transient condition, how what part of the landscape is changing more drastically as compared to other parts.
Makes sense. Thank you for answering that.
I don't see any new questions in the chats, and it's about noon, so I think with that we will wrap this up. And as a reminder, this is our last EPSP Connects event of the year. We will not have one in December, but many of us are going to AGU, and we hope to see you there. We are expecting to have an event in January. We're working on that now, but we cannot quite yet announce what that is. But keep an eye on your email for updates about that. So thank you, Dr. Singh, again for a great talk. And yeah, we hope to see many of you at AGU.
Yeah, thank you very much.